Welcome to another CSI analysis program. Here at CSI, we are seriously committed to the success of your reliability-based maintenance programs using predictive and other proactive maintenance methods. When diagnosing problems, spectral data gives a lot of information, but sometimes key elements are missing from the spectral data. Instead, these key elements are often found in waveform data. For this reason, it is extremely important for you, the analyst, to be able to use the waveform data to confirm or pinpoint the source of any problems. Applying the tips and techniques of this program, detailed waveform analysis, will enhance your RBM program, increasing uptime and saving thousands of maintenance and downtime dollars. Whether you use multi-channel analyzers or single-channel analyzers, a good understanding of waveform data and how it affects spectral data increases your ability to accurately determine the root cause of vibration, as well as the severity of any problems. This program reviews how a waveform is created and transformed into a spectrum, as well as the differences in the various waveform units. We will show how occurrences in a machine are reflected in the waveform and spectral data. Other topics include how to use waveform characteristics to distinguish certain faults. What is modulation and what does it tell you? How is modulation represented in spectral data? And how to collect the waveform that gives you the most information for a thorough analysis. In a previous program, Introduction to Vibration Analysis, we used an unbalanced tire to show how a waveform is simply a trace of a machine's movement over time. Notice that as the wheel turns 90 degrees, the trace also moves relative to the center line. A 90-degree rotation in the tire from the top corresponds to a movement in the trace from the top to the center line. Another 90 degrees is from the center line to the lowest point of travel. Another 90 degrees is from this lowest point back up to the center line. The final 90 degrees rotation of the tire moves the trace from the center line to the top point of travel. This angular relationship is called phase. It is important to understand this phase relationship as it will help us later in determining some waveform characteristics. Although this example traced a tire's rotation, we typically measure the back and forth movement due to the rotating mass. This vibration can be compared to the movement of a spring mass system. The up and down motion of this mass is similar to the directional vibration of a machine due to imperfections in the rotating mass. If a pen is mounted on the moving mass and paper is pulled past it, a trace of the movement is recorded on the paper. This trace is like the trace of the unbalanced tire. Let's look at the waveform generated from this motor that has an unbalanced condition. Notice that it is smooth and very repetitive with a sinusoidal shape. Since we know that one rotation is equal to one complete sine wave, we expect the time between two of these peaks to equal the time it takes for the rotor to turn once. When we place this phototack so that it sees a mark on the rotor, the speed is shown as 1756 RPM. This is 29.3 Hertz. This frequency can be calculated from the waveform using a method derived by a French physicist, Baron Jean-Baptiste Fourier, who lived from 1830 to 1928. Late in his life, he proposed that the complex waveform could be represented by the sum of individual sine waves and cosine waves of varying frequency and amplitude, and separated by their repetition rate to create a spectral view of the same data. In other words, each repeating sine wave could be separated, and the time for each cycle of the sine wave determines the discrete frequency of the sine wave. The process allows these individual waveforms to be viewed from the end at its discrete frequency, and is called a spectrum. Although Fourier was scorned for this concept, it was later proven accurate, and a modified method of his process was named in his honor. It is called the fast Fourier transformation. Thus, the common name for the spectrum is abbreviated to FFT. The mathematical conversion from a sine wave to the spectral view is done simply by dividing the time for one complete cycle into one. This obtains the inverse of the number. For this waveform, the time between the cycles is 34.2 milliseconds, or 0.0342 seconds. Dividing this number into 1 yields 29.3 cycles per second, or hertz. This value is displayed on an FFT plot as a frequency of 29.3 hertz, or 1756 cycles per minute. This spectral data is commonly used in vibration analysis to determine problems and the severity. However, recall that the Fourier transform is valid only on repeating sine waves and cosine waves. This means that some information may be in the waveform and not in the spectral data. It is important, therefore, to examine the waveform content as compared to the FFT. The waveform is really a continuous signal that the vibration sensor sees. But most of today's analyzers are digital units, which mean they use an analog to digital or AD conversion to manipulate and store the data. The analog signal then must be sampled with enough points to store a good representation of the actual waveform. This waveform is a stored digitized waveform. The actual stored points have been connected by lines, but the cursor only lands on the digitized stored points. Some machines generate a dominant frequency such as this, but most machines generate multiple frequencies. The effect of multiple frequencies can be seen using the single-channel analyzer, a CSI Model 2115 machinery analyzer. We will look at two independent signals, then combine them to demonstrate the effect of multiple waveforms. The first signal is from the same rotor kit with a dominant unbalanced condition. Notice that this is not a smooth sine wave, but has other energy riding on it. The second signal is from a signal generator. The input frequency is 20 Hz and is a smooth sinusoidal waveform. The two signals combined show the amplitude variations as the signals add and subtract from each other, creating a more complex time waveform. This example showed the waveform data in acceleration. In another program, Introduction to Vibration Analysis, we use go-karts to demonstrate that a waveform can show three precise measurements. The displacement measurement is the total distance traveled from one peak to another. The greatest speed or velocity is at the midpoint, and the greatest acceleration is at the turning points of the waveform as the direction changes. Each measurement of displacement, velocity, or acceleration can be displayed as a separate waveform simply by displaying the maximum velocity or acceleration at the top of the waveform. Remember that industry standards measure peak to peak on displacement waveforms, zero to peak on a velocity waveform, and the RMS value for an acceleration waveform. Earlier we pointed out that there is a 90-degree change from the zero line to the positive peak and 90 degrees from the zero line to the negative peak. When comparing the three waveforms, notice that the velocity waveform does not overlay the displacement waveform, but is ahead of it. The maximum velocity occurs 90 degrees before the maximum displacement occurs. Velocity is then said to lead displacement by 90 degrees, or that there is a 90-degree phase difference between velocity and displacement. The acceleration waveform leads the velocity waveform by 90 degrees. Maximum acceleration has a 90-degree phase difference from maximum velocity, and a 180-degree phase difference from maximum displacement. We'll use data from this small rotor kit that has an unbalanced condition to demonstrate this phase relationship. The phototac gives a constant reference signal as we display the incoming data from the sensor in the 3 units on this multi-channel analyzer, a CSI Model 2400 4-channel analyzer. The square wave on the screen is the reference signal from the phototac. One revolution is from one square wave to the next. The smooth sine wave is a displacement sine wave from the sensor. Notice how this displacement sine wave lines up with the square wave. The velocity waveform is now shown, and the relationship from the reference pulse is 90 degrees from the displacement waveform. With the acceleration waveform shown, notice the relationship to the reference signal. It is a full 180 degrees from the displacement waveform and 90 degrees from the velocity waveform. The concept of the phase relationship among the 3 waveforms is an important one to know and can help you understand the necessity of using the same units throughout the procedure, such as a balance job. Let's compare the information the 3 waveforms tell us. This displacement waveform indicates an unbalanced condition in this machine. It is smooth and very sinusoidal, with no other energy apparent. The same measurement point in velocity still has a predominant 1 times sinusoidal waveform, but has other energy that could be multiples of turning speed. The acceleration waveform of the same point shows much more energy present with high-frequency energy. It is important to note that these 3 measurements are made from the same measurement point with the same measurement point setup. Since acceleration is directly proportional to force, as Newton's second law proves, the energy shown here is related to the force of any impacting that may be occurring in the machine. Since this impacting can be such a destructive force, it is usually best to store and examine the waveform in acceleration units to have the most information. Waveform energy is made up of multiple sine and cosine waves, which can be separated into individual frequencies using the fast Fourier transformation and displayed as a spectrum. Although the analyst can derive a lot of information from the spectral data, the waveform in acceleration can hold information that is not transferred to spectral data. In the previous section, we showed the importance of the waveform and the information it contains. We need to be aware, though, that the waveform may have limitations due to the limitations of the analyzer that can mask some critical problem. It is important to set up the measurement to obtain the information you need. We have pointed out that most of today's analyzers are digital and actually only store points that are then connected to show a representation of the actual waveform. If the analyzer stores 1024 sample points for a particular waveform, it has twice the information that a 512 sample point waveform has for the same data. The importance of the number of sample points can be demonstrated using this analyzer to monitor a rotor kit. Setting the sample size to 1024 points and monitoring the waveform, notice all the detail of the waveform with the energy showing random impacting. Now changing the number of sample points to 256 will have only 1/4 as many points in the waveform. Notice the waveform is fairly smooth without much indication of impacting. It is much more difficult to accurately determine the condition of the machine with this little information. The number of sample points is typically referred to as the waveform resolution. Some analyzers store a maximum of 1024 points, while some have the capability to store more than 16,000 points for a waveform. For most routine analysis, 1024 points provide the information needed to make an accurate diagnosis. With adequate waveform resolution, you will be able to pick out certain patterns in the waveform to determine whether the energy is periodic with repetitive energy, complex and varying, impacting with random or repeating spikes, or has discontinuities, or is asymmetrical and has truncation, whether there is influence from process or electrical frequencies, whether there are low-frequency events or modulation. Let's consider each of these waveform characteristics in detail and the effect it produces in the spectrum. The spectral data from this unbalanced rotor kit is a distinct peak at the frequency of the shaft speed. The peak is very narrow and does not have a wide skirt at the bottom. This indicates that the waveform is dominated by a single frequency. Viewing the waveform in displacement units, we see that it is indeed smooth, sinusoidal, and repetitive. The amplitude from peak to peak is the same as shown in the spectral data. The waveform in acceleration units is more complex due to the energy from high-frequency impacting riding on the 1 times sine wave due to the unbalance. But the waveform is still dominated by the single frequency due to the unbalance. Periodic repetitive waveforms can be at the turning speed of the shaft or its multiples. This motor generator set is misaligned, and the waveform is very repetitive, but not all the amplitude is the same. This is because there are actually 2 sine waves, with one of them being stronger than the other. We expect the spectral data to have 2 peaks then, with one being higher in amplitude than the other. Although these 2 examples show synchronous energy creating a periodic waveform, non-synchronous energy can also generate a periodic waveform. This waveform has a repetitive pattern, but appears much different than the previous examples. The vertical lines mark the shaft turning speed. Notice that there are 3 events that occur during some shaft revolutions, and 4 events in others. This indicates that although the source of this energy is repetitive, it is not synchronous or a harmonic of shaft turning speed. This is an example of energy generated from a non-synchronous bearing frequency or from another component in the machine which has a different shaft speed. This spectral data may appear to be very similar to the spectrum generated by a periodic signal because there are several multiples of turning speed present. A closer look reveals other information. These peaks have a wider base or skirt and are raised off the floor. This is not usually the case with very periodic energy. One look at the waveform and we see it is not anything like the waveform energy due to unbalance or misalignment. Instead, it is very complex and busy, with non-repeating or random impacting energy. This energy is from a looseness condition that is causing components to rattle against each other, creating many frequencies. A complex waveform may include many of the waveform characteristics discussed in this section, such as asymmetry and truncation or severe impacting. Recall that the fast Fourier transform process separates individual sine waves and displays them as discrete frequencies. With this much energy, there will usually be sine waves equal to the turning speed frequency as well as its harmonics. The remaining energy may add noise that includes all frequencies and therefore raises the base floor of the spectrum to some amplitude. An impact hammer is usually used for resonance testing, and the accelerometer response is measured to determine the resonant frequencies. In this case, however, we will only measure the instrumented force hammer and capture the energy of a single impact. A single impact imparts all the frequencies, but does not have any repetition. Remember that Fourier's basic premise states that the complex waveform is the sum of harmonics of the repetition rate. In an impact, there is no repetition rate, so this creates a problem. Energy occurs at all frequencies, and there is only one point in which they are all in phase to add together to produce the pulse shown in the waveform. The resulting spectrum does contain energy at all the frequencies, but no single dominant frequency. The net result is a continuous spectrum and is often referred to as a raised floor. Again, the waveform data has the most useful information. In acceleration, these impacts are proportional to the force. When 2 or more impacts occur, the waveform data shows each impact as we would expect. Each of these 3 impacts produces a single non-repeating pulse which imparts all frequencies and creates a continuous spectrum. However, since there are 3 impacts exciting all frequencies, these frequencies will be in and out of phase, adding and subtracting frequencies spaced at the repetition rate of the impacts. This waveform is from a blower that has an outer race defect on the bearing. It has severe impacting to plus and minus 7 Gs, but notice the pattern is very repetitive. When the waveform is expanded, we can mark one impact and move to another. The time between the impacts is about 18.5 milliseconds. This approximates a frequency of 54 Hz. The spectral data shows multiple peaks that have wide skirts. Setting the primary cursor on the peak at 54 Hz, we see that the harmonic cursors fall on top of the peaks. Although the impacts in the waveform are spaced at an interval equal to 54 Hz, the energy shows up as multiples of the frequency. This is due to the FFT process, which adds a series of sine waves that are exact multiples of the repetition rate of the signal creating the harmonics. To Fourier's credit, we can see that the transformation from the waveform to the spectrum reduced the complex time waveform to its individual sinusoids. In this case, the impacting is much more evident in the waveform, and its repetition produces harmonics in the spectral data. In a single impact, all frequencies are present, but because there is no repetition, there is no distinct frequency in the spectral data, but appears instead as a raised floor. Multiple random impacts also cause a raised floor and can generate harmonics of a frequency. This waveform is very unconventional and indicates specific conditions. Remember that this is a digitized waveform, and the stored information is actually dots. The lines simply connect the dots. This means that as the waveform data was being sampled, something changed abruptly in either the machine or the instrumentation. Data with discontinuity usually indicates a loss of the input signal. In this case, a sensor cable had broken, causing the intermittent signal and the radical change in the data. The spectral data has a high peak, nearly 7 inches per second at a frequency of 5 Hz. The rest of the spectrum appears as a raised floor, much like random impacting. Although the spectral data does not appear normal, it could be overlooked. But the waveform data immediately tells the story of an intermittent signal. This data was acquired during a routine monthly survey. If the program had been defined to keep only spectral data, this waveform, which provided the key to the diagnosis, would have been discarded. It is important to store the time waveforms during routine surveys. This waveform is from a slow-turning chain-driven roll. Notice how it is very asymmetrical. That is, there is much more energy on one side of zero than the other. In this case, the predominant energy is on the positive side. The asymmetry indicates that motion in one direction is limited, and there could be an obstruction. Or by design, the system may allow more freedom of movement in one direction. There appears to be some random impacting in the waveform. From the previous section on spikes and impacts, we know to expect to see a raised floor of the spectrum. But the asymmetry due to a restriction of motion clips or truncates the waveform in one direction so that it no longer is a pure sine wave at a single frequency. Remember Fourier's basic premise for a complex waveform. It is the sum of the harmonics of the repetition rate of sine and cosine waves. This is transformed to the spectral data as harmonics of shaft turning speed. The cursors mark the shaft turning speed harmonics. The other peaks are 1/3 and 2/3 harmonics. Another example of asymmetry involves a severe truncation due to a restriction of motion. This waveform data is from an unbalanced condition of a spindle that is mounted so that it moves easier in one direction than the other. Again, the restriction causes a clipped waveform that is no longer a pure sine wave at a discrete frequency. The FFT process adds the series of sine waves, which are the exact multiples of the signal generated from the turning speed. The resulting spectrum has turning speed harmonics. If we were to view this spectrum to determine the cause of the problems, it would be unclear. However, one glance at the waveform tells the story. This is another example of the value of using the waveform to aid in diagnosis. The source of problems can sometimes be difficult to detect. In motors, for instance, vibration can be caused by mechanical events such as imbalance, misalignment, mechanical looseness, or the vibration can be caused by electrical problems such as an uneven air gap, rotor bar problems, shorts in the windings, and others. Oftentimes, there is more than one forcing function in a machine, and two of the forcing functions may be so close together they appear as one frequency when the resolution is not adequate to separate them. A technique often used to determine the amount of energy attributed to electrical phenomena is to shut off the power while monitoring the data. Electrical energy will immediately drop out, while mechanical energy will remain through the coast down. The coast down can be monitored in the spectral or waveform data. Here we are using a single channel analyzer to monitor the waveform. Set the maximum frequency and sample size to capture the data, being sure that the sample time will not cause the shutoff to be missed. The fast update rate of the waveform helps ensure capturing the change as the machine is shut off. Notice the drop in amplitude as the electrical energy is removed from the waveform. This indicates that nearly half the energy is attributed to electrical events. When the coast down is monitored in the spectrum, the data is only as good as the update rate of the analyzer. In other words, as the waveform is sampled, the process time to perform the FFT and display the spectrum may cause the actual shutoff event to be missed. While the machine is running with a load, there is some fluctuation in the signal. Without adequate resolution, the multiple frequencies may appear as one, and the drop-off due to electrical energy may not be as noticeable. In this case, we see that there is substantial change in the spectral data as the machine is shut off. But to be certain to capture the event, the waveform will typically show the most information. Events that occur a few seconds apart are missed by many analysts, and problems that stem from these events can take an analyst by surprise. These events can occur in speed reduction gearboxes or may occur in typical pumps, fans, and motors due to process variables or transient events. Normal routine data collection on typical equipment may not capture low-frequency or transient events. Equipment that has turning speeds of 30 to 60 hertz may have only an eighth to a half second of time in the waveform. The length of time in the waveform is defined as the sample size divided by the maximum frequency times 2.56. The sample size is the number of data points in the waveform. In some analyzers, the maximum number of points is 1024. Other analyzers may be able to store more than 16,000 data points for the waveform. The maximum frequency is the highest frequency to be included in the waveform or spectral data. Routine data collection may include frequencies to 50 times shaft turning speed. If the shaft speed is 60 hertz or 3600 RPM, the maximum frequency will be 3000 hertz or 180,000 cycles per minute. 2.56 is a constant. This is how much faster the data must actually be sampled to achieve anti-aliasing of the signal. With 3000 hertz as the maximum frequency, the time window in the waveform is only 133 milliseconds or 0.13 seconds. Remember that there are 1024 data points in this waveform. This means there is extreme detail for the 0.13 seconds. However, a short time waveform cannot capture multiple occurrences of low-frequency events spaced even a half second apart. If the maximum frequency is set to 200 hertz and the sample size remains at 1024 points, then the time in the waveform is a full 2 seconds. This new waveform data from the same machine running in the same condition shows much more information. There is a repetitive cycle occurring approximately 5 times during the 2 seconds. This was not evident in the waveform that had a maximum frequency of 3000 hertz. Expanding the 2-second waveform of the 200 hertz data allows us to check the time differential between the low-frequency events. We see that the time for one event is 0.4 seconds. This time is equal to a frequency of about 2.5 hertz. The 3000 hertz spectrum with 400 lines of resolution has a minimum frequency of 15 hertz. This event cannot be seen in the spectrum at its fundamental frequency. It has been left out of the spectral and waveform data. The spectral data from the 200 hertz data has 400 lines of resolution, but includes energy down to 1 hertz. The 2.5 hertz is very low in amplitude and will typically be overlooked. However, this low-frequency event is observed in the spectrum. The cause of this frequency is discussed in the next section entitled Modulation. In routine PDM surveys, most measurements are set to include high-frequency data to be sure to capture early stages of bearing wear and other high-frequency energy that can be so destructive to a machine. However, these measurements could be missing low-frequency occurrences that may be the root cause of the bearing failures and other high-frequency energy. Some analysts include at least one low-frequency measurement on each machine component to capture these low-frequency events. For very slow-speed machinery, that is, below 200 RPM shaft speeds, time waveforms may need to be as long as 1 minute to capture transient or very low-frequency events. This data is over a 4-second period. The event occurred once every 2 seconds with a half-second duration. The problem in the machine would have been more difficult to find and diagnose without a long time span in the waveform. Two types of modulation seen in vibration analysis are amplitude modulation and frequency modulation. A third phenomenon, beat frequencies, are often mistakenly thought of as modulation. Modulation is the product of two frequencies, a carrier frequency and another frequency, whereas a beat frequency is two primary frequencies that add to and subtract from each other. Let's examine the waveform and spectral characteristics for each of these phenomena. In the previous section, we used this motor generator set to illustrate the importance of collecting a time waveform that captures low-frequency events. The pattern in the waveform of these low-frequency events is commonly assumed to be modulation. In reality, these may be beat frequencies or true amplitude modulation. An example of a beat frequency is seen in these two independent frequencies that are fairly close together. The frequency of one signal is adjusted to line up with the other signal. As the individual frequencies repeat, they will be in phase and out of phase with each other. As they move in phase with each other, their amplitudes add together, causing an increase in amplitude. As they continue, they will move out of phase with each other until the phases are opposite. And at this point, the amplitude of the two frequencies subtract from each other. This varying amplitude as the frequencies move in and out of phase creates an audible droning sound, which is a beat. Usually a longer time in the waveform is required to capture these beat frequencies. This 2-second time waveform captured 5 cycles of the beat frequency. In the previous section, we measured these and determined that the time for each repeat was 4/10 of a second, which is a frequency of 2.5 Hertz. The area around 120 Hertz is expanded to show two distinct peaks 2.5 Hertz apart. The peak at 117.5 Hertz is exactly 2 times turning speed, and the peak at 120 Hertz is 2 times line frequency. The sidebands result from the beat of two primary frequencies, each having harmonic content. This beat frequency is also present at the difference frequency of 2.5 Hertz. Beat frequencies are common when primary frequencies are less than 4 Hertz apart. Now let's look at frequency modulation. In this example of a gearbox, the carrier frequency is gear mesh frequency. Pure frequency modulation maintains a constant amplitude signal with frequency variations. As commonly seen in industry, gearboxes exhibit both amplitude and frequency modulation. The sideband spacing around the gear mesh frequency is the input shaft speed. Gears have tooth spacing variations which cause the speed of the gear to constantly increase and decrease. This causes the frequency modulation. The gears on this shaft have 48 teeth. The high impacts are spaced at the shaft turning speed. As expected, the expanded waveform shows 48 impacts during each shaft revolution. The waveform data clearly shows the significant 1 times turning speed event. This is a result of amplitude modulation, which is more dominant in this example. The 1 times turning speed peak is present in the spectral data. However, its amplitude is very low and could have been missed by the analyst. As a result of the modulation, this event shows up as sidebands spaced at shaft speed around the gear mesh frequency. Gear mesh frequency is the carrier frequency in gears. Frequency modulation is due to speed variations causing frequency changes. In amplitude modulation, the frequency remains constant and the amplitude varies, causing sidebands around a carrier frequency. These changes in amplitude could be from repetitive load changes in synchronous motors or generators. They could also occur in rolling element bearings as the defect passes in and out of the load zone. Amplitude modulation typically has only one sideband to each side of a carrier frequency, in contrast to frequency modulation, which will have multiple sidebands. However, most applications in industry are a combination of both frequency and amplitude modulation. The number of sidebands is relative to the nonlinearity in the system. The amplitude and frequency modulation differ from beat frequencies in that the beat frequencies are closely spaced primary frequencies, which add and subtract, while modulated frequencies are the product of two frequencies and show up as sidebands around a carrier frequency. The defect frequencies are the carrier frequencies in a rolling element bearing. Waveform data is often the key to diagnosis that might not have been evident from spectral data alone. Whether simple or complex, random or periodic, asymmetrical or truncated, waveform characteristics can truly provide helpful information, which leads to a more confident diagnosis of misalignment, looseness, rolling element bearing defects, gear defects, electrical, and other machinery problems. View the waveform and acceleration to assist you in the analysis. Remember that decreasing the maximum frequency and increasing the sample size increases the time waveform length, allowing very low frequency events to be captured. However, increasing the maximum frequency and decreasing the sample size provide more detail for high-frequency events. We are confident that by applying the principles in this program, your vibration analysis skills will be enhanced. Thank you for selecting CSI for your PDM and RBM needs. We look forward to helping you achieve success in your future endeavors.